Welcome back to Igneous and Metamorphic Petrology. This video continues the discussion of metamorphic facies by focusing on facies associated with the metamorphism of mafic rocks. Because Escala defined metamorphic facies in the bases of metamorphosed mafic rocks, we'll use these rocks as we look more in depth at the types of mineral changes and associations that develop, increasing metamorphic grade along temperature, pressure gradients, characteristic of the three facies series discussed in the previous videos. In the present context, mafic rocks include volcanic rocks from basaltic to andesitic in composition, gabbros and diorites plutonic rocks, and immature mafic greywackies. Metamorphosed volcanic rocks are by far the most common volcanic parent rocks that occur in a wide variety of tectonic settings. Most of the common metamorphic minerals in mafic rocks exhibit extensive solid solution, so that metabasalts or metabasalts tend to have fewer phases than metapelites or pelites, protoliths. This results in fewer reactions in isograds, which is one of the reasons why Escala chose to define his facies on these rocks, since they resulted in broader subdivisions and made it easier to categorize and correlate different areas. Hydrous minerals are not common at high temperature mafic igneous minerals, so hydration of mafic rocks is a requirement for the development of mafic mineral assemblages. Unless water is available, mafic rocks will remain largely unaffected by metamorphism. Coarse-grained intrusives are the least permeable and most resistant to metamorphism, whereas tuffs and greywackies are more susceptible. Hydration reactions are strongly exothermic, and estimates suggest that the breakdown of clinopyroxene and plagioclase to prehnite, chlorite, and zeolites can raise the temperature of a system by as much as 100 degrees Celsius. When water is present, this reaction tends to run to completion. As we discussed in our discussion of mafic rocks, mafic protoliths are chemically and texturally complex and variable. As a result, the facies series discussed here are simplified. The natural systems are susceptible to variations in bulk rock composition, fluid availability, and relative abundance in water and carbon dioxide. We consider metamorphic reactions to be continuous, and as a result, the grade at which a particular mineral appears or disappears during prograde metamorphism may vary from rock to rock and location to location. Many reactions discussed that govern metamorphism of mafic rocks are illustrated in figure 26.19 in the Metamorphic Reactions chapter. You may want to refer to this figure during the remainder of this video. Most common minerals in mafic rocks are solid solution series, and as a result, metabasalts have fewer phases than pelites and contain fewer reactions in isograds. The principal mineral changes in metabasalts are due to the breakdown of two common mineral phases in basaltic rocks, plagioclase and clinopyroxene. Calcium-rich plagioclase progressively becomes unstable at lower temperatures. General correlation between temperature and maximum anorthite content of stable plagioclase, lower temperature metamorphic grades tend to favor albite, with anorthite contents of 0 to 3. Upper green schist facies tend to favor oligoclase, and anorthite contents jump from 1 to 7 to 17 to 20, what we refer to as the platistite solvus. Andesine and more calcic plagioclase become stable in upper amphibolites and granulite facies. The excess calcium in aluminum can produce calcite, an epidote mineral, sphene, amphibole, and other minerals, depending on the pressure, temperature, and composition. Clinopyroxene will react to various mafic minerals, including chlorite, actinolite, hornblende, epidote, and metamorphic pyroxenes, as well as others. The mafic minerals that form are commonly diagnostic of metamorphic grade and facies. Amphibole compositions may be particularly informative as a facies indicator for some grades. Initial assessment of low-grade metamorphic rocks were written off as altered and did not receive much attention from petrologists. Very low-grade metabasites or basalts are usually the only partly altered to very fine-grained and messy-looking minerals. It wasn't until Boyles and Coombs recognized systematic patterns in these rocks and showed that they could be studied in the same way as other metamorphic rocks. The zeolite facies rocks are a prime example of this difficulty. In zeolite facies, volcanic glass is altered to hyalinite or stilbite, along with other phyllosilicate minerals. Crystalline phases, though, remain essentially intact. Because these phases are stable under diagenic conditions, some petrologists consider the stabilization of limonite to be the first metamorphic phase. The prehnite-pompelliite facies begins with the limonite disappears and prehnite-pompelliite quartz begins to appear. The ACF diagram is typically used to depict the mineral assemblages associated with the zeolites and pompelliite facies, as well as the other facies we're going to talk about with metamorphic mafic rocks. Most mafic rock compositions occur in the shaded field in the pinkish color on the ACF diagram. A typical zeolite facies of this composition will contain a mineral assemblage of chlorite, hyalinite, calcite, quartz, and albite. The transition to prehnite-pompelliite facies is marked with the loss of hyalinite and the addition of prehnite and or pompelliite. The crossing tie lines in this facies, the prehnite-pompelliite facies, results from combining the low-grade prehnite-bearing zone and the high-grade pompelliite actinolite zone on the same diagram. Pompelliite disappears as the rock enters the green schist facies, where the phase is replaced entirely by actinolite and epidote. As mentioned previously, if no fluids are present in the system, facies in lower grade than green schist are not always present in metabasalts, but where present, they can be valuable in understanding the metamorphic history of the rocks. The green schist, amphibolite, and granulite facies constitute the most common facies series of regional metamorphism. The classical Bavarian facies series of pelitic zones and the low-pressure Buchanan-Akpumana series are variations of this trend. The zeolite and prehnite-pompelliite facies are not present in the Scottish Highlands, and metamorphism of mafic rocks first evident in the green schist facies, which correlates with the chlorite and biotite zones associated with pelitic rocks. Typical minerals include chlorite, albite, actinolite, epidote, quartz, and possibly calcite, biotite, and silamine. Chlorite, actinolite, and epidote impart a green color from which the mafic rocks and the facies get their name. Although some schists are not green schist facies and may be green, it is not common, and the green schist and green stone rock names should only be applied to the rocks of this facies. The ACF diagram for a typical metamorphic assemblage in metabasalts is shown in figure 25.7. The most characteristic mineral assemblage is chlorite plus albite plus epidote plus actinolite plus quartz. The transition from green schist to amphibolite facies involves two major mineralogical changes. Albite goes to oligoclase, and actinolite goes to hornblende. Both transitions occur approximately at the same grade but have different pressure-temperature slopes. The reaction that generates calcic plagioclase and hornblende are complex, and a continuous reaction involving the breakdown of epidote and chlorite to supply the calcium and aluminum. The transition to more calcic plagioclase consumes the epidote, and as pressures increase, the temperature of the calcitic plagioclase reaction appears to increase more than the temperature of the reaction responsible for the actinolite to hornblende reaction. As a result, hornblende typically occurs before calcic plagioclase. Metabasites, or basalts, in the amphibolite series are characterized by the assemblage of hornblende plus plagioclase, plus lesser amounts of quartz, epidote, garnet, clinopyroxene, and or biotite. Amphibolite facies corresponds generally to the upper garnet, starlite, kyanite, and lower silmonite zones of associated pelitic rocks, as we'll discuss later. Figure 25.8 is the ACF diagram for metabasalts in the amphibolite facies, illustrating the typical assemblage in the shaded area. Because hornblende is a solid solution series, much of the compositional area for the mafic rocks is within the two-phase hornblende plagioclase field. The transition from amphibolite to granulite occurs somewhere between 650 and 850 degrees Celsius. In the presence of fluids, associated politic and quartzo-feldspathic protoliths begin to melt in this range at low pressures, resulting in fibrillite facies being the final facies before melting for these rocks. Mafic rocks generally melt at much higher temperatures, and granulites are common at high grades for metabasalts. Hornblende is typically the last remaining hydrous phase and will decompose into orthopyroxene and clinopyroxene. The granulite facies is characterized by the presence of largely anhydrous phases. The critical assemblage is orthopyroxene plus clinopyroxene, plagioclase, and quartz. Garnet is also a common phase, and minor hornblende and biotite may be present at low granulite grades. Note that the basalt has been progressively metamorphosed from a green schist to a granulite facies, has returned to a mineralogy dominated by plagioclase and pyroxene, just like the original basalt. The textures, however, is generally going to be gneissic, and the grain shapes are desiccate or polygonal, thus bearing no resemblance to the original basalt. Figure 25.9 illustrates the typical mineral assemblage of the granulite facies for a mafic rock. Miyashiro in 1994 noted that although a single pyroxene metabasalt can occur in the granulite facies, they are not particularly useful. This is because clinopyroxene is a common low aluminum, high calcium phase in mafic rocks and amphibolite facies. In high magnesium iron metabasalts, cummingtonite, an amphibole phase, may break down to orthopyroxene at low temperatures, and this can occur before hornblende breaks down, resulting in an orthopyroxene bearing amphibolite. The origin of granulite facies rocks is complex and controversial, but there is general agreement, however, on 2 points. 1. Granulites represent unusually hot conditions. Temperatures have to be above 700 degrees Celsius, and geothermometry has yielded some very high temperatures, even in excess of over 1,000 degrees Celsius. Average geotherm temperatures for granulite facies depths should be in the vicinity of 500 degrees centigrade, suggesting that granulites are the products of crustal thickness and excess heating. Second, granulites are dry. Rocks don't melt due to the lack of availability of water. Granulite facies terrains represent deeply buried and dehydrated roots of continental crust. The mineralogy of low-pressure metabasites is not appreciably different from medium-pressure facies series. Albite epidote hornfels facies correlate with the green schist facies, into which it grades with increasing pressure. Hornblende hornfels facies correlates with the amphibolite facies, and the pyroxene hornfels and sandodite facies correlate with the granulite facies. For now, this will conclude our discussion on metamorphic facies. We're going to come back to this idea after we discuss pressure, temperature, time paths, and introduce the idea of metamorphic reactions. And at that time, we will discuss high temperature, pressure series of the blue schist and eclogite facies. These series will make more sense once we discuss the metamorphic reactions.